Diamagnetic materials create an induced magnetic field in a direction opposite to an externally applied magnetic field, and are repelled by the applied magnetic field. In contrast, the opposite behavior is exhibited by paramagnetic materials. Diamagnetism is a quantum mechanical effect that occurs in all materials. When it is the only contribution to the magnetism, the material is called a diamagnet. Unlike a ferromagnet, a diamagnet is not a permanent magnet. Its magnetic permeability is less than μ0, the permeability of vacuum. In most materials, diamagnetism is a weak effect, but a superconductor repels the magnetic field entirely, apart from a thin layer at the surface. Diamagnets were first discovered when Sir Justinus Bergmans observed in 1778 that bismuth and antimony were repelled by magnetic fields. In 1845, Michael Faraday demonstrated that it was a property of matter and concluded that every material responded to an applied magnetic field. He adopted the term diamagnetism after it was suggested to him by William Whewell. Materials. Diamagnetism, to a greater or lesser degree, is a property of all materials and always makes a weak contribution to the material's response to a magnetic field. For materials that show some other form of magnetism, the diamagnetic contribution becomes negligible. Substances that mostly display diamagnetic behavior are termed diamagnetic materials, or diamagnets. Materials called diamagnetic are those that laymen generally think of as non-magnetic, and include water, wood, most organic compounds such as petroleum and some plastics, and many metals including copper, particularly the heavy ones with many core electrons, such as mercury, gold and bismuth. The magnetic susceptibility values of various molecular fragments are called Pascal's constants. Diamagnetic materials, like water, or water-based materials, have a relative magnetic permeability that is less than or equal to 1, and therefore a magnetic susceptibility less than or equal to 0. Since susceptibility is defined as chi-V equals μV minus 1. This means that diamagnetic materials are repelled by magnetic fields. However, since diamagnetism is such a weak property, its effects are not observable in everyday life. For example, the magnetic susceptibility of diamagnets such as water is chi-V equals 3 quintillion 5 quadrillion 95 trillion spade suit minus 9.05 times 10 minus 6. The most strongly diamagnetic material is bismuth. Chi-V equals 3 quintillion 3 quadrillion 834 trillion spade suit minus 1.66 times 10 minus 4. Although pyrolytic carbon may have a susceptibility of Chi-V equals 3 quintillion 3 quadrillion 600 trillion spade suit minus 4.00 times 10 minus 4 in one plane. Nevertheless, these values are orders of magnitude smaller than the magnetism exhibited by paramagnets and ferromagnets. Note that because chi-V is derived from the ratio of the internal magnetic field to the applied field, it is a dimensionless value. All conductors exhibit an effective diamagnetism when they experience a changing magnetic field. The Lorentz force on electrons causes them to circulate around, forming eddy currents. The eddy currents then produce an induced magnetic field opposite the applied field, resisting the conductor's motion. Superconductors may be considered perfect diamagnets because they expel all fields due to the Meissner effect. However, this effect is not due to eddy currents, as in ordinary diamagnetic materials. Demonstrations. Curving water surfaces. If a powerful magnet is covered with a layer of water, then the field of the magnet significantly repels the water. This causes a slight dimple in the water's surface that may be seen by its reflection. Levitation. Diamagnets may be levitated in stable equilibrium in a magnetic field, with no power consumption. Earnshaw's theorem seems to preclude the possibility of static magnetic levitation. However, Earnshaw's theorem only applies to objects with positive susceptibilities, such as ferromagnets and paramagnets. These are attracted to field maxima, which do not exist in free space. Diamagnets are attracted to field minima, and there can be a field minimum in free space. A thin slice of pyrolytic graphite, which is an unusually strong diamagnetic material, can be stably floated in a magnetic field, such as that from rare earth permanent magnets. This can be done with all components at room temperature, making a visually effective demonstration of diamagnetism. The Radboud University Nijmegen, the Netherlands, has conducted experiments where water and other substances were successfully levitated. Most spectacularly, a live frog was levitated. In September 2009, NASA's Jet Propulsion Laboratory in Pasadena, California announced they had successfully levitated mice using a superconducting magnet, an important step forward since mice are closer biologically to humans than frogs. They hope to perform experiments regarding the effects of microgravity on bone and muscle mass. Recent experiments studying the growth of protein crystals have led to a technique using powerful magnets to allow growth in ways that counteract Earth's gravity. A simple homemade device for demonstration can be constructed out of bismuth plates and a few permanent magnets that levitate a permanent magnet.